One more method is again related to Gibbs free energy itself. Change in Gibbs free energy is equal to minus RT ln K. You also know this particular expression, which is related to equilibrium constant. So K is equilibrium constant, isn't it? R refers to universal gas constant, T is temperature, delta G naught is change in Gibbs free energy, standard change in Gibbs free energy. So using this expression also, if we know the equilibrium constant for any the reaction if we are carrying out, then if we know the equilibrium constant of that particular substance, we substitute here and check out whether delta G is negative. If delta G is negative, then what does it mean? That means the reaction is feasible or the reduction is feasible. This is a part. This comes under thermodynamic principle. Now here the most important concept in this unit again, which we know, it's like interesting concept we can say. A scientist by name H.J.T. Ellingham, he said or he explained this particular concept of thermal reduction. He said, I have plotted a graph, and using that graph you can find out easily which substance can be used as reducing agent. So then it was very interesting to know again, like just by looking at a graph, if you know which can be a very good reducing agent, it's the best thing, right? So he said, I have made it. And here we have this Ellingham diagram. So in this Ellingham diagram, as you can see, I have the graph is of delta G naught versus temperature. Ellingham diagram is a graph of delta G naught versus temperature. Using this interpretation, the choice of reducing agent or choice of good reducing agent can be known. What does it help to know? It helps us to know the good reducing agent for reduction. Our main idea is we have already converted the substance into oxide, we want to reduce it. So just look at this particular diagram. This Ellingham diagram is given for oxides. Ellingham diagram also, you can find Ellingham diagrams for carbonates, for sulfides also. This is given in your syllabus. So just have a look at it. This is delta G naught values here and delta T values along the x-axis, just given. So here it is 0 degrees Celsius, 400 degrees Celsius, 600 degrees Celsius, 800, 1200, 1600, 2000. You can also convert it into Kelvin scale also. Here as you can see, observe, here it is 0. Below 0, these are all negative values. It's minus 100, minus 200, minus 300, minus 400, up to minus 1200 is given. Which one? Delta G naught value, Gibbs free energy in kilojoule per mole. As you can see, here I have drawn some straight lines. The graphs are straight lines, and at some point you can see there is change. The line just deviates or there is transformation taking place. What it is all? Remember Ellingham diagram, first point which you need to know is, in Ellingham diagram, the graphs are straight lines. Straight lines with some phase transformations. Somewhere you can see phase transformations taking place. PHASE it is, phase transformations. Phase in the sense solid, liquid or gas. State transformation. It can be like solid getting converted into liquid, or liquid getting converted into solid, or liquid getting converted into gaseous state, or vice versa. So phase transformation can take place. See here for example, a graph you can see it was a straight line and it has deviated. That means at a particular point phase transformation has taken place. Rest of the lines, most of the lines you can see they are all straight lines. Apart from for few, here zinc oxide curve you can see at a point it has again deviated. That means phase transformation. Maybe from solid to liquid state it has deviated, and so that particular curve you can see in that way. That's one point. See here, this is for magnesium getting converted into magnesium oxide. This is aluminium into aluminium oxide, zinc to zinc oxide. Here carbon to carbon monoxide to carbon dioxide curve it is. This is iron oxide curve. This is copper oxide curve. This is carbon dioxide curve. Few important ones are mentioned here. Now, how do you know which can be used as reducing agent? See, the ones which has higher or large negative values are highly stable. So, which one has large negative values, which are at the bottom? They are highly stable. So, what does it give information? Oxides with, that means metal oxides with large negative G0 value, delta G0 values are highly stable. If they are highly stable, that means they can act as good reducing agent. Which can act as good reducing agents? Like, see, now for example, I'll tell you, zinc oxide is here above. Magnesium oxide is below. That means magnesium oxide has high negative delta G0 value, large negative delta G0 value. So, magnesium can be used as good reducing agent to reduce zinc. Got the point now? And see, now zinc is at the bottom. Copper is at the top. If you want to reduce copper, which can you choose? You can either choose zinc, or you can choose aluminium, or you can choose magnesium, since they have large negative value. So hope the concept is clear. The lines lying below are highly stable and can reduce the substances or oxides that are above it. Metals of this can reduce the above metal oxides easily. Clear now? So that is the concept of Ellingham diagram. Okay, just have a look at it. And to speak about this Ellingham diagram, it is given in the yellow bar of the textbook. Most of the time they don't ask question from that part. So for the knowledge sake and to know much about the concept, you can have a look at this particular diagram. Okay, have a note, then we'll move on to the next part of it. Let me tell you one more thing here. It's about the limitations of Ellingham diagram. Yeah, Ellingham diagram helps us to know about the choice of reducing agent, but it too has limitations. The limitations are, see, we know about thermodynamic concepts related to reduction, but it does not tell whether the reaction is faster or a reaction is slow. Reduction process is fast or slow. That means chemical kinetics is not explained. Chemical kinetics is not explained, or Ellingham diagram does not give information about the chemical kinetics of the reaction. And the considering of the equations, that is delta G is equal to delta H minus T delta S, or delta G naught is equal to minus RT ln K, it may not be always true. Because you know, sometimes there is phase transformation taking place, solid to liquid, there can be phase transformation. Then what happens? Entropy changes, order completely changes. If it is solid, it is highly ordered. If it is liquid, slightly it is disordered compared to solids. So here the values may change. And here related to equilibrium constant also. Always you cannot depend on this particular equations to know. So which are the two limitations? One is about chemical kinetics. The other one is the expression of delta G naught is not always applicable. And yeah, one more thing here. See here, I have shown you a point of intersection here. That means, see, maybe at around 1200, about 1200 Kelvin, you see aluminium oxide curve and magnesium oxide curve intersects. That means they bypass. Aluminium oxide passes this way and magnesium oxide above that. That means you must always remember temperature condition is also very important to know. Below this particular temperature, magnesium can reduce aluminium. But above that temperature, now you see aluminium is down or below and magnesium is above, which can act as a good reducing agent. Above a particular temperature, now aluminium can reduce magnesium. Okay, that also must be considered. So if you are clear with it, we'll move on to the next part. Next we shall see, though there are limitations of Ellingham diagram, there are few applications of it, important applications also. We'll see which are they. Okay. One important application, that is, we are studying applications of Ellingham diagram. Applications of Ellingham diagram. Briefly, if you check out the curve, see, I have roughly drawn an Ellingham diagram, that is few parts from Ellingham diagram. So the first application of Ellingham diagram is extraction of iron. Extraction of iron. How iron can be extracted? By using Ellingham diagram principles. So here I have drawn curves. This is carbon-carbon monoxide line. That means carbon getting converted into carbon monoxide, that line. And here carbon monoxide and carbon dioxide line. And here we have iron and iron oxide line. What do you get to know from this? And here, say the temperature is around 1073 Kelvin. That means, you see, below 1073 Kelvin, which line is, now we want to reduce iron oxide. Iron is this line. Below that, which line lies below it? It is carbon monoxide. But carbon is above, so we can't use that as reducing agent. But carbon monoxide line is lying below. So carbon monoxide can be the best reducing agent below 1073 Kelvin. So which is one point? Below 1073 Kelvin, carbon monoxide can be a good reducing agent. Whereas you check out after above 1073 Kelvin, this carbon monoxide line crosses FeO line and it goes above. Now FeO line is below. So can you use carbon monoxide again as a reducing agent? No. Then you see here, this is iron oxide line, which is below carbon and carbon monoxide line. Carbon getting converted into carbon monoxide line is below. So above 1073 Kelvin, coke is the best reducing agent, that is carbon is the best reducing agent, but below 1073 Kelvin, carbon monoxide is a good reducing agent. So what is the point? Above 1073 Kelvin, coke is a good reducing agent. Coke is a good reducing agent. Hope this is clear. The choice of reducing agent is clear. That means at low temperature, carbon monoxide can be a good reducing agent, but above a particular temperature, that is 1073 Kelvin, coke can act as a good reducing agent. This we get to know from this. Now let us move on to the most important part of this extraction process, that is the diagram part. I'll just draw a rough diagram here. Okay, we'll see the parts of this. So this is a area where the ore particles will be subjected. This is a part for exhaust gases. Here you can see two inlets through which blast of air and oxygen will be passed. This is an area for molten slag. This is area for molten iron. And here pig iron will be collected, and here slag will be collected, that is molten impurities. And here the temperature ranges are 1070 Kelvin, 1270 Kelvin, 1570 Kelvin and 2170 Kelvin. This is a rough diagram of the furnace which we use here, which is called as blast furnace. Now let us study the processes taking place here. So hope this is clear, the choice of reducing agent. Let us see the reactions taking place. Now you can see the furnace which I have drawn, which is called as blast furnace. Here what happens, there is a cup and cone arrangement here, this particular arrangement. It's just a rough diagram which I have drawn. You can just refer the diagram for this. Here through the inlet, ore of iron along with limestone and coke. Coke means carbon is introduced. Okay, so what is the first step? The first step is where ore limestone and coke mixture altogether we call it as charge, CHARGE. This is fed, the mixture is fed into the blast furnace. The name blast furnace is because we are going to blast air and oxygen from the bottom of it, and that is why it's called as blast furnace. Now here what happens? Ore you have taken, why you have taken limestone is a question now. Ore can be either hematite or magnetite, Fe2O3, or magnetite Fe3O4. Oxide ore usually will be considered. Now here what happens? One more we have taken limestone, isn't it? What is the role of limestone? Limestone acts as flux. Why it is added is because to remove impurities, in the form of slag. Slag means the molten form of impurity along with this flux. Flux plus impurity gives slag. Remember this. So why we have added limestone? Limestone is nothing but CaCO3, calcium carbonate, to remove impurities in the form of slag. Now what is the role of coke? Coke acts as reducing agent. You know why we are using coke as reducing agent, and we know the condition. Below 1073 Kelvin, that is at low temperature, carbon monoxide will act as reducing agent, and above 1073 Kelvin, coke will be acting as reducing agent. So this is clear, this part is clear now. Now let us see what chemical reactions takes place at different zones. This is again important. Either they will ask you the extraction of iron using blast furnace, otherwise they will ask you to write the chemical reactions or equations involved in the process. So hope this thing is clear. We'll move on to the next part. So here the chemical reactions we'll see first at a low temperature. At low temperature, that is 500 to 800 Kelvin. At this temperature, how the reactions takes place. Here what happens? What we have taken the ore Fe2O3. It reacts with carbon monoxide, because we know at low temperature carbon monoxide acts as reducing agent. What do we get? Either it can be converted into Fe3O4, one possibility, along with the liberation of carbon dioxide. This is one possibility. So here it is 3. I'll make it 3. 3 2s are 6. So we will write 2 here. Clear? Here 3 3s are 9, plus 1 10, 4 2s are 8, 9 10, balanced. The other possibility is now this Fe3O4 formed further reacts with carbon monoxide. Now here this carbon monoxide reacts with this oxygen to form carbon dioxide. It liberates. What is left out? Iron is left out here. Iron 3 Fe. So here 3 Fe. Then check out for oxygen. Oxygen is 4 here, but here it is only 2. So I'll make it 2 here. 2 2s are 4. Here carbon 1. So 2. Hope it's clear now. Okay. Here Fe which we have got, this iron is called as pig iron. Why it is called as pig iron? Because in the earlier days when they used to convert the iron which is obtained here into different forms, they used to give shapes to it. It resembled like that of piglets. And that is why it was called as pig iron, which contains 4% of the carbon impurities. That I will tell you later. So hope this is clear now. And one more possibility is Fe2O3, than converting into Fe3O4, it can also convert into iron oxide also. This is also a possibility. It can also convert into iron oxide. So again try balancing it. Here it is 3 plus 1 4, here 2. So 2 plus 4, 6. Here 3 plus 2. Here it becomes 4. Fe2, Fe2, here 3, here 2. Just try balancing it. Okay, this is at low temperature. Now let us see the reactions taking place at high temperature. Please do note this. We'll move on to the reactions taking place at high temperature. So here, as you remember, this reaction, because we need this FeO to convert it into Fe later. At high temperature, what happens? At high temperature, say at around 900 to 1500 Kelvin. Here we have taken limestone there, isn't it? Limestone is calcium carbonate. On heating, it decomposes. Decomposes in the sense it breaks, the bond breaks and forms carbon dioxide by liberating carbon dioxide. In different processes, you can see carbon dioxide being evolved. Why that is used? That increases the temperature in the blast furnace, whichever is required for the further reactions to take place. Now we have got calcium oxide, isn't it? This calcium oxide is going to react with the impurities. Impurities is what? Silica, which will be present as impurity. So it forms calcium silicate, CaSiO3. So you can see calcium carbonate is flux plus impurity, which is giving you a slag. They can ask you a question, which is a slag formed in the extraction of iron. It is calcium silicate. There is one more equation which you need to remember. Here, now at this point, carbon also reacts with oxygen to form carbon dioxide, which again increases the temperature. So till here it is clear. Now we had got FeO here, isn't it? In the previous process, what happens? It reacts with coke and forms Fe plus CO, which is again the pig iron which we have got. This is the process of extraction of iron.